Today we're going to be talking a little bit about the applications of wave behaviors before we get into any calculations with refraction. That'll happen next class. So the first one is reflection, which sounds pretty basic, but there's actually some pretty decent applications of this that were worth discussing. The first one of those is parabolic reflectors. Parabolic reflectors allow the waves that come in to focus to one exact point, which very much strengthens the signal that you get, whether it be light rays, radio waves, sound waves. Spherical reflectors, like if this is a spherical mirror, the rays that come in towards the center of the mirror, they will reflect to a very specific focal point, but the rays that come in at the edges here and here, as you get further away from the center, the focal point changes, and what that would result in, if it was an image, it would be a blurry image. If it were a signal, such as a radio signal, it would not be as strong because the signal is being focused at different points. An application of that, here we've got a radio telescope, and the radio telescope takes radio waves that would be too faint to detect otherwise with any real resolution, and all those waves that are coming in reflect, and they meet at this specific focal point, and that's where you put the detector, and that creates a much more intense and stronger signal and allows you to actually have good resolution and a good enough signal to be able to see the images that you're trying to find with the radio waves. Now, something closer to home would be a satellite TV. Same basic concept though, as the satellite signal comes in, too weak to detect by the detector all by itself, but when it comes in and reflects back at the focal point, then that is a much stronger signal, and that allows you to get the signal that you need for your TV. And then a cool application of this is a solar death ray. And so if we take a quick look at this, this is a solar death ray that was being constructed by a high schooler. He went ahead and posted it, and what he's doing, he's taking the piece of wood and he's putting it at the focal point, and you can see when he gets it at the exact focal point the effects there. Let's go ahead and magnify that. So as you saw, when he was at the focal point, that's where the rays were all focused at one specific spot. So the rays that were coming in all over, all that energy was focused in one specific spot and resulted in a much stronger signal. In this case, a light signal, and that energy all being focused in one spot created a whole lot of heat. Another example, if you kind of work in reverse, is if you put a wave source at the focal point and you've got a parabolic reflector behind it, that would allow you to send the waves back and reflect out fairly straight. So headlights take advantage of that. If you want to have focused headlights, you want a parabolic reflector behind the headlight, and that will help focus the beam straight ahead. Another example of reflectors is something called retroreflectors, and these are pretty cool because what these allow you to do is to have any rays that come in, due to the geometry, we have three 90-degree mirrors here, so no matter what angle the light comes in, it'll always reflect straight back to the light source. So light coming in from this way will reflect straight back, light coming in from this way will reflect straight back. You see things like this on really reflective surfaces, like the attachments they have to bikes, to the reflectors they have on bikes, on your shoes, reflective tape that you might put on a jacket that you are jogging in at night. Street signs tend to have this reflective quality. And so right here, this is an example of a retroreflector, and you'll notice that at the very center, the camera that was taking the picture, that's where the lens is. It seems to appear from the center. Now the interesting thing is, no matter where you go, when you're looking at this, you would always, the camera lens would always appear at the center, no matter what angle he's trying to photograph it at, because it's always reflecting the light straight back to the source. And one of the more extreme examples of this is on the moon. During the Apollo missions, they laid down retroreflectors on the moon, and with very high energy lasers from Earth, we can actually beam the laser to the moon and then get a reflection back. Because this reflects it straight back to the source, we're able to measure the distances between the Earth and the moon. And as time has gone on, they've gotten that distance more and more accurate as technology has improved, down to the point where it's accurate to within 1 inch, which is pretty good considering that the moon is about 250,000 miles away. Another example of reflection is sonar, radar, or LiDAR. LiDAR is one you may not be as familiar with. Sonar sends sound signals and allows you to get an idea where the object is and how far away it is based on the echo that you hear. So underwater submarines and boats, they have sonar that can detect objects in the water. Bats rely on sonar. They send out very high frequency sound pulses. Those sound pulses can reflect off the bugs, which is what they survive off of mostly, and that allows them to not only tell how far away they are, but also the direction they're located, and something we go in a little bit later with Doppler effect, could also tell them if it's coming towards them or after them, depending if the reflected sound wave happens to be higher pitch or lower pitch. So here's an echo example problem. This is pretty basic, pretty easy, something we'd expect you to be able to solve. If you are standing in front of a tall canyon wall, so you get a good distance, when you clap you hear a reflection a fraction of a second later. If you can estimate the speed of sound, which is usually right around 340 meters per second, it can get faster if the temperature is warmer. But if you clap your hands and about 0.4 seconds later you hear your echo, you can estimate the distance to the wall. And so basically this ends up being a column 1 problem, because the speed of sound is going to stay pretty constant. So this would be speed equals distance over time, but we're rearranging it because we're looking for the distance. We know that the time is 0.4 seconds. We know the speed of sound is around 340 meters per second. So what distance would that be? If you plug your numbers into the formula, distance equals speed multiplied by time, then what we have is 136 meters, but you have to remember that's the distance that it took for the sound to travel to the wall and back to you. So that's actually double the distance to the wall. So what we do there is we can actually divide that distance in half. So half of 136 would be 68 meters. That would be the distance away from you if it takes you about 0.4 seconds in order to hear your echo. Another application is the lenses for refraction, and probably the easiest to relate to the example here is when you have trouble seeing, if you're nearsighted or farsighted. What happens here is, if this is your eye, you have light detecting cells which are called rods and cones, and they are on the inside of your retina, which is the very back of your eye where the light comes in and falls. In this example, the light is being focused not on the retina but behind the retina. So right here where the retina is, things are out of focus because not all the images are focusing in the exact same spot. And so if you have a corrective lens here, this type of lens tends to squeeze the light together a little bit more, tends to make it come in and focus before it goes through your lens, which allows it to focus at a closer spot, which is right along your retinal wall. Down here, this person, their focal point is before it gets to the retinal wall. And so by the time the image gets here, it's all spread out along the retinal wall. And that would again result in a blurry image. So they have a different type of lens, which instead of focusing the light, it tends to spread the light out. So, but then by the time it goes to your lens, it is focused now on the retinal wall. So this is the difference between if you are farsighted or nearsighted. Another application of refraction that comes into play in your life is fiber optics. Now what fiber optics do is they take advantage of something called total internal reflection. So down here, we talked about refraction. If you come in straight along the normal line, there is no bending the light. You just, as you go from a slow medium to a fast medium, it would just slow down but not bend. But when you approach at an angle, as you go into the fast medium, the angle between the light rays and the normal line becomes greater. And if you approach at a steep enough angle, At this angle, the light is refracted so much it just skims along the surface, and at any angle greater than that, you have what's called total internal reflection, where it bends the light so much that it actually reflects back inside the material. And that's what fiber optics do. Here we have a light shining into a fiber optic, and as it goes through the fiber optic, it just reflects inside over and over and over again until it hits at a different angle, and then it's able to come out. And the reason why we want to go ahead and use fiber optic cables is because compared to the old cable companies, which used coaxial cable, combination of metal and some other materials, fiber optic cables can carry much greater data loads every second. So you can carry more signals, you get more data traveling every second. It's much faster, and as it turns out, it's lighter and cheaper. Another application of refraction is ocean waves. And one thing that you should know is that as water travels along the ocean, as the surface below the ocean gets shallow, so basically you're coming towards the coast, more shallow water the waves tend to move slower. And so right here what we have is we have some waves traveling in this direction. Where there is an object right here making the water more shallow, you see the wave pattern, but where the water is deeper, what you'll notice is it starts out all in the same spot, but the water that's deeper, and therefore the waves traveling faster, you see that the waves get further and further ahead compared to the waves over the more shallow region. So again, in shallow water the waves travel slower, but in deep water the waves tend to travel faster. And this would explain what happens when you're at the beach and you see the waves breaking. Instead of the waves just coming in, they start piling on top of each other. So in deep water, everything's pretty spread out and things are going pretty fast. But as the water gets more shallow, as it approaches shore, the fast-moving water behind starts piling up on top of the slower moving water, and that makes the waves get taller and taller until eventually they start falling over each other, and that's what you call a breaker. And those are the waves that you're familiar seeing at the water park. Another example of wave refraction is in prisms. If you've ever wondered why a prism spreads the light out into a rainbow, you've been told since elementary school that white light is composed of all the different colors of the rainbow. So that's Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. And Roy G. Biv is the order that they happen to occur in. When you take a look at the rainbow that's formed here, you see violet on one end, red on the other, and it goes in the order red, orange, yellow, green, blue, violet. What you probably may not know is that the different frequencies of light determine the color. So violet has a short wavelength at a high frequency. So of the visible light you can see, it has the shortest wavelength. And then as you go towards red, it becomes the longer wavelengths. And what happens in light is as it gets refracted, there is a slight difference in how the short wavelengths get bent or refracted compared to the long wavelengths. And as it turns out, the shorter wavelengths get diffracted more. It's an effect called dispersion, how the different wavelengths get diffracted at slightly different angles. So as the white light comes in and goes through the prism, it gets refracted and then gets refracted again. The light gets spread out, and so what you see is that red gets bent the least, so it ends up being on top. And as you go down the order of the rainbow from red to violet, violet being the shortest wavelengths gets refracted the most, and that ends up being on the opposite side. And that's why the colors of the rainbow are always in the order they're in. Another wave property I wanted to discuss is diffraction. Now with diffraction, we slightly discussed this last time, but light waves and sound waves have very different wavelengths. And as it turns out, it's very short wavelengths at high frequencies do not bend as easily around objects as long wavelengths. So in this case, you have a person coming around the corner. Light, being a very small wavelength, does not bend around the corner very easily, and so you cannot see the person around the corner due to the very small bending of light due to diffraction. However, sound is a much longer wavelength, so even though you may not be able to see around the corner with the short wavelength light rays, you can hear around the corner with the very long wavelength sound wave. So you can hear someone around the corner even though you cannot see them around the corner. The sound waves do a better job of bending or diffracting around the barrier. Now an example where this could come into play is with bats in echolocation when they're using sonar emitting sound frequencies to locate their food source, which is primarily insects. So bats, you have to use very, very high-pitched sounds in order to detect these insects. And the reason for that is, at very short wavelengths, high frequencies, then the waves have a better chance of reflecting off the small insects and coming back so the bat can detect them. If the bat were to emit lower frequency sounds, which are longer wavelengths, then the sound would do more diffracting around the object and less reflecting back to the bat. Now, if you look up online, you get some different numbers. But in general, it's agreed that bats typically emit frequencies between 40,000 and 200,000 hertz when they're doing echolocation. Whereas a typical human speech frequency is somewhere between 80 hertz and 180 hertz. So if we just kind of average these values, for bats I just took somewhere in the middle, 100,000 hertz, and for humans somewhere in the mid-range, about 120 hertz, just so we could see what would the wavelength be. So for bats at 100,000 hertz, somewhere in the middle of what they can emit. If you talk about your wave equation, velocity equals frequency times wavelength, and you rearrange that, again, speed of sound being about 340 meters per second in air, the frequency of the bat's sonar signal, rearrange the equation for wavelength, that'd be speed over frequency, and so when you do the math, plug in the numbers, you get 0.0034 meters, which is about 0.34 centimeters, about 1/3 of a centimeter, which is maybe on the range of 1/4 of an inch or less. So those will do a better job of reflecting off small insects. A human voice, if we take a frequency of about 120 hertz at the same speed of sound, plug in those numbers, we get about 2.83 meters, which is close to 3 meter sticks long, 283 centimeters. Those sound waves will most definitely bend around small objects such as insects, and the echo heard would be indistinguishable and would not be of use during echolocation, hence the need for higher frequencies during echolocations for small objects. Another behavior of waves that we're going to discuss is interference, and the first example for these applications is sound canceling headphones. So what we have here is a situation where the headphones actually have a microphone in them that detects noises from the outside. Now, in order to cancel out that sound, you need to send the opposite signal. So this is the outside noise as we have crests and troughs coming in, and then as it enters the speaker, a little bit of computation from the microprocessor, and it sends the exact opposite signal out, which you see here in red. So when the outside noise comes as a trough, it can send a crest, and then as the outside noise is a crest, the speakers can send a trough. And what happens when you have the exact opposite signals? They exactly cancel each other out. You have destructive interference. And so that noise is, if you have good quality sound canceling headphones, pretty effectively canceled out to get rid of that outside noise. Another application is called two-point source interference. And in this picture what you see is you have two different points that are hitting the water, creating circular waves. So you have 2 point sources of waves. And as the waves travel over and through each other, they're going to interfere. Now, I'm not quite sure how well you can see it on camera. We have a better example here in just a moment. But if you look closely, you can see lines, for example, here and here and here, where this waves are destructively interfering. These are spots where the waves are continuously encountering crests versus troughs, and so this is lines of destructive interference, and in between those are constructive interference. So this is a more two-dimensional view of the waves in a stream, which would be one-dimensional when they interfere. Now, the easier to see pattern here is a simulation. But again, you got the two circular waves being formed, and where they overlap, you have constructive or destructive interference. So remember, where they add together constructively, we call that an antinode. So this is where the water waves would be going up and down quite a bit. This is a node, which is destructive interference, where you always have crests and troughs interfering. So if this is sound, what you would hear is loud sound, soft sound, loud sound, soft sound. If this was light having these interference patterns, you see bright light, dim light, bright light, dim light. And if you had two speakers playing the exact same note, and you were to move around the room, and if we were in class, I would demonstrate this for you, you could actually hear the sounds where spots in the room where the sound is louder and spots where the sound is quieter. a interesting application of that is what happens if the sounds are not exactly the same frequency? What if they're off by just a little bit? Well, in that case, we get what we call a beat pattern. Now, if you play an instrument and it's here at school, so you're playing with other people who are playing the same instrument as you, you may have noticed this when you're all tuning your instruments. If you have two people who are slightly out of tune from each other, the frequencies will sometimes overlap and constructively interfere, and then as one frequency happens more often than the other, they'll pass each other up and they'll destructively interfere. So what we see here, right here, we have crests overlapping with crests, and so you get constructive interference, the sound gets loud. But if one of these frequencies is a little bit off, eventually you start having crests line up with troughs, and they cancel each other out, and this sound gets quiet again. But then as they continue to mismatch, they line back up and you get crests on crests again. So again, the sound gets loud, soft, soft. And we've got an example of this. This is more of a one-dimensional example. Let's go to the two-dimensional examples that we have. So this is where the frequencies are exactly the same, what we were talking about a few minutes ago. And so you have these patterns of destructive, constructive, destructive, constructive interference, but you notice they're staying in the same place. Now, what happens if we make one of these frequencies a little bit different? And so that's what we have going on here. And so what you notice here is that the constructive and destructive interference spots are moving. So let's say this point right here is where you're standing. You'll see that you have loud, soft points going past, and that's what this shows right here is a more one-dimensional view we were just viewing, which is as the waves destructively, then constructively, then destructively interfere with each other, you hear the sound getting loud and soft and loud and soft. Now you can actually try this yourself right through your computer speakers. You type in online tone generator, and there's more than one site that does this. But what we have here is a generator that's playing at 441 hertz frequency, so it sounds like this. I'm going to turn that up a little bit so you can hear it more clearly. And here we have a 435 hertz frequency. Now that sound's going to be very, very similar. You probably can't even tell the difference. However, what happens when we play them together, these are different between 441 and 435 hertz. These are different by about 6 hertz. And what you'll notice, that means that the beat frequency, they'll line up and then unalign 6 times every second. So you hear a beat frequency, a pattern of loud and soft tones happen 6 times a second if I played them at the same time. Now what happens if I want them to be a little bit closer to each other? Well, I can go ahead and change this to 438. And what you notice there is the beat frequency is happening less often. The difference between 438 and 435 is obviously only 3 hertz, so therefore the beat frequency was just happening 3 times per second, 3 loud and soft patterns each second. And so this is the equation. If you want to go ahead and find beat frequencies, it would just be the absolute value of the difference between the frequencies. So it doesn't matter which one you plug in first. You take the difference between them, regardless if it's positive or negative, you just report the positive answer. So what we were just doing, 435 hertz and 441 hertz, what's the beat frequency? Well, you got the 2 individual frequencies. You're looking for the beat frequency. So that would be the absolute value between the frequencies. So the difference between these two is negative 6 hertz, but the absolute value of that is just plain 6 hertz. And the last application of waves we're talking about is going to be for absorption. And for this one, I just picked sound absorption. I don't know if you've ever moved into a new house, but I remember when we moved into our first house, my son, who's a sophomore now, was about 1.5 at the time. And our house looked a lot like this, which it had hardwood floors, no furniture. And when he ran around, he literally did this. He started squealing because he heard his echo, and it was a little new and different for him. So he ran around in circles from room to room, just making noise and hearing his echo. Well, the next day when we brought him back, we had moved in the furniture. He tried the same thing again, and as soon as he did it a few times, he stopped and he looked really confused because what had happened is we'd furnished the room. We put in couches, we put in some carpeting, we put in some drapes, and all these materials absorb the sound. And so what that did is reduce how much sound bounces around the room, and he no longer heard his echo. If you ever travel back and forth between LC and LN, it's been a while since I've been at Lawrence Central, but last time I was there, they still had carpeted hallways, and one of the things I definitely noticed is that Lawrence Central's hallways tend to be noticeably quieter, not because the kids are talking any less, but because at Lawrence North we have solid walls and tile floors, so the sound really echoes around and carries. Whereas at LC with the carpeted hallways, they have sound absorbing carpet, and that simply makes the noise travel not as far, it gets absorbed as it echoes, and the hallways end up being more quiet. And now, a place where you may use this would be at a sound recording studio. At a sound recording studio, high quality sound recording studios will have sound absorbing materials to help prevent echoes, help prevent distortions. So regardless of whether you're having an interview or you were recording live music, the sound quality is going to be much higher because you don't have any extra distortion coming in from the echoes coming around the room. It is absorbed by the materials laid upon the wall.